Did you know that supermassive black holes hiding at the center of galaxies are responsible for their incredible energy emission? In the second part of the AGN series, we continue exploring other active galaxies such as quasars and blazars and their role in the evolution of galaxies. Let's begin. A subclass of distant AGN with extremely luminous centers are known as quasars. A quasar's radio emission may come from radiolobes or jets. They are FR2 sources. Quasars are so far away that in optical images they show up like bright stars with a faint halo around it, which may be resolved into the parent galaxy for a few of them. It goes without saying that to be visible at such great distances, quasars must be very powerful. Quasars are believed to be a consequence of high-velocity gas spiraling into the central supermassive black hole of the host galaxy. The host galaxies of quasars often have disturbed morphology as shown in these examples. The faint disk of the galaxy surrounding a very bright nucleus shows up on the images with very long exposures. To get an idea, picture the fact that a typical quasar has a luminosity of around 5 into 10 to the power 39 watt, which is approximately 100,000 times brighter than the total power of a large galaxy like the Milky Way. In general, the spectra of an AGN is quite flat relative to thermal sources such as stars or a galaxy made up of stars as shown here. Most quasars also emit quite a lot of ultraviolet light, leading to this feature called the blue bump in the ultraviolet and optical wavelength region of the spectrum. This is sometimes accompanied by a smaller infrared bump leftward of the UV bump, which may be due to dust grains with temperatures below 2000 Kelvin. The AGN spectrum turns over at a frequency of around 5 into 10 to the power 12 Hz due to dust or synchrotron self-absorption. Historically, AGN were believed to have very flat spectra and hence a formulation of this form was used. Notice the y-axis in the plot. Such plots for AGN are always plotted as log nu versus nu log f nu. That is because the power received from a source in any frequency interval nu and nu plus delta nu can be then rewritten as this integral, so that equal areas under the curve correspond to equal amounts of energy. Now we know that AGN spectra are formed by a combination of thermal and non-thermal emission. Thermal emission means the emission from sources such as stars which follow a black body spectrum and are mostly unpolarized. The non-thermal emission, on the other hand, originates from highly polarized sources and follows a power law spectrum. As the name suggests, this emission is independent of the temperature of the source. In astronomy, we encounter three main types of non-thermal emission. Of these, the synchrotron radiation is most important in the context of AGN. The synchrotron radiation are generated by electrons spiraling around the magnetic field lines at relativistic speeds. Since the electrons are continuously changing direction, that is accelerating, they emit photons of frequency corresponding to the speed of electron at any given instant. This radiation is confined to a narrow cone pointing in the direction of the motion of the electron. This process is called beaming. This radiation is also polarized in a plane normal to the magnetic field. The spectrum of the synchrotron emission results from the emitted spectra of individual electrons. As an electron continues to spiral around the magnetic field lines, it emits at a range of frequencies, peaking at a critical frequency, nu naught. Let's look at the AGN spectra in detail. Shown here is the spectral energy distribution of the quasar 3C273. It spans over 15 orders of magnitude in frequency. A horizontal line on this plane will represent a spectral index of 1. Usually, the spectra falls off quickly at the low frequency end, but 3C273 has a larger than average spectral index of 0.24 in this regime. That is because the spectrum is dominated by jets at low frequencies. The peak output of this spectrum is in the low energy gamma ray waveband, but for other quasars, it could be in the infrared or X-rays. Besides emission lines like the ones we discussed for Seyfert's, absorption lines are also found in the spectra of quasars. Doppler broadened absorption lines are found in around 10% of quasar spectra. These originate from sources with speeds exceeding 10,000 km per second. These lines are usually associated with the quasars. However, other narrower high redshift absorption lines observed in spectra of quasars are due to the Lyman series of hydrogen and metals such as carbon and magnesium. These absorption lines with rest frame wavelengths in the ultraviolet waveband are often redshifted into the optical region of the spectrum due to the recessional velocity of the absorbing material. The absorption lines in a quasar spectra can therefore be placed into different groups with common redshifts and are almost always less than the redshift of the quasar. These lines are due to the absorption of high-energy radiation from the quasar by hydrogen clouds which lie along the line of sight between quasar and the observer. Quasars and other active galactic nuclei are believed to be powered by gravitational accretion onto supermassive black holes, where supermassive means roughly 1,000,000 to a few billion times the mass of the Sun. Supermassive black holes reside at the center of almost all large galaxies. In about 5 to 10% of these galaxies, gas tumbles into the deep gravitational well of the black hole and is heated to incandescence as the gas particles gain speed and pile up in a rapidly rotating accretion disk close to the horizon of the black hole. It rotates in order to conserve angular momentum. Remember the M87 black hole observation? The bright ring-like structure is actually the accretion disk. The supermassive black hole is much smaller on the scales of this image. The distinguishing factor between an active galactic nuclei and a normal galactic nuclei is that the black hole of an AGN accretes a few solar masses of matter every year. In addition to black holes and accretion disks, quasars have other remarkable features. For instance, just beyond the accretion disk are clouds of gas that move at high velocities around the inner structure. These clouds absorb high-energy radiation from the accretion disk and reprocess it into broad emission lines of hydrogen and ions of other atoms that are the signatures of quasar spectra. Farther from the black hole, but still within the plane of the accretion disk, are dusty gas clouds that can obscure the quasar itself. AGN, whose nucleus is visible and the spectra shows both narrow and broad emission lines, are classified as type 1, while AGN, whose broad line region is obscured by a torus of dust and the emission lines are narrow, are labeled as type 2. Some astronomers believe that type 1 and type 2 AGN are intrinsically the same objects. The broad lines observed in the AGN spectrum are created in the broad line region close to the center of the galaxy. The width of these lines cannot be due to thermal broadening because the typical widths observed would require temperatures of the order of 10 billion Kelvin. But at such temperatures, all the atoms will already be ionized, so no emission lines are possible. Therefore, assuming the lines are Doppler broadened, the gas emitting these lines must have a large-scale velocity of around 10,000 km per second. Such high velocities imply a strong gravitational field in the vicinity of the gas and is therefore considered an evidence in support of the presence of a supermassive black hole at the heart of AGN. The broad lines provide clue to the density and temperature of the gas found here. Note that only allowed and semi-forbidden transitions are possible in the broadline region. Sophisticated analytical models have now made it possible to calculate the total volume of the broadline region and the volume of the emitting gas. The ratio of these two suggests that the emitting gas fills up less than 1% of the total volume of the broadline region, implying that the emitting gas must be present in the form of clouds. Almost all AGN show narrow emission lines in their spectra, which originate in the narrow line region. The narrow line region lies beyond the broad line region. The lines corresponding to this region are around 400 km per second in velocity width, which is narrower relative to the lines produced in the broad line region, but still broader than the emission lines observed in normal galaxies. Besides Lyman alpha and carbon 4, the forbidden line oxygen 3 at 5007 angstrom is the strongest emission lines observed in the narrow line region. The very existence of forbidden lines implies that the density of gas in the narrow line region is significantly lower than in the broad line region. The temperature of the narrow line region is also somewhat lower than the broad line region, and the filling fraction of gas is small, once again implying that the gas must be present in the form of clouds. Observations of nearby AGN have revealed that the narrow line region is not symmetric around the center. In fact, the ionization is strongly dependent on the direction because the shape appears to be two cones on either side of the center as seen in the Seyfert galaxy NGC 4151. Quasars are often found at very high redshifts. For instance, the Sloan Digital Sky Survey recorded more than 500 quasars above redshift 4. At such high redshifts, the Hubble law should not be used for estimating distances because the total elongation of the wavelength depends not just on the distance traveled by light, but also on how the expansion of space has changed over time. That is why usually redshifts are mentioned for high redshift objects such as quasars and not their distances. But remember that the fractional change in the wavelength of light is the same as r, the fractional change in the size of the universe as shown here. This implies that a quasar at redshift of 3 means that the universe is now 4 times larger than it was when the light was emitted from the quasar. Active galaxies with strongly variable, highly polarized non-thermal continuum are known as blazars. These objects are characterized by a featureless spectra and are highly variable in luminosity in different wavebands. Blazars are further classified into BL-lac objects and OVVs. BL-Lacarta or BL-lac objects are known after the prototype galaxy of this class, the BL-Lacarta, found in the constellation of Lacarta, which literally means the lizard. Deep images have now confirmed that 90% of BL-lac objects, including the prototype BL-lac, is the nucleus of an elliptical galaxy. Most BL-lac objects have very weak or absent emission lines in their spectra, as a result of which their redshift remains unknown. The spectra of BL-lac objects is also characterized by strongly polarized power-law continuum. BL-lac was originally classified as a variable star because of irregular variation in its brightness, which varied by a factor of 2 over a week and a factor of 15 in few months as shown here. Such a plot of luminosity versus time is called a luminosity curve. In general, the luminosity of BL-lac objects can vary by up to 30% in just 24 hours and by a factor of 100 over a longer time period. BL-lacs showing variation in radio wavebands are called radio BL-lacs or RBLs. Similarly, those variable in X-rays such as 3C279 shown here are called XBLs. The top panel in this figure shows variability in X-rays while the bottom panel represents gamma rays. Note that the luminosity varies by a factor of 10 in a matter of few days. Another subcategory of blazars is the OVVs, the optically violently variables. They are similar to BL-lacs except that they are typically more luminous and have broad emission lines in their spectra. Their luminosity is variable at wavelengths other than optical as well. OVVs are strong emitters of radio radiation. Low ionization nuclear emission line region or liners are galaxies with low luminosity nuclei but strong emission lines of low ionization species. Their spectra is similar to low luminosity C4 galaxies. In fact, liner-like emission can be detected in most spiral galaxies, starbursts, and even H2 regions, and therefore it remains a topic of debate if this is even a real class of AGN. Liners are the most well-known amongst AGN because liners and CFERs can easily be classified based on the emission lines present in the optical spectrum of a galaxy. Such a diagnostic plot of emission line ratios was first used by Baldwin, Philip, and Terlevich in the year 1981 and are therefore popularly known as the BPT diagram. As long as all 4 emission lines required for any of the diagnostic plots are available in the optical spectra, it can be confirmed if the emission comes from star formation, AGN-like emission, or a sum of both. The latter are justifiably known as the composite galaxies. The BPT diagnostics is a popular method among optical astronomers for distinguishing AGN and star-forming galaxies for samples where spectroscopic data are available. A common picture of AGN which has emerged in this discussion is that the central engine of an AGN is a rotating accretion disk orbiting a rotating supermassive black hole. This engine converts gravitational potential energy into synchrotron radiation. The rotational energy of the supermassive black hole may also play a critical role in this process. To supply the amount of energy observed in emission, an AGN must accrete 1 to 10 solar masses of mass per year. The orientation of the AGN with respect to the observer, the mass of the supermassive black hole, and the rate of accretion of mass onto that black hole primarily determine whether it is classified as a CFERT1, CFERT2, BL-lac, radio-loud, or radio-quiet quasar. Although several aspects of this unification theory are still debatable or less understood, observations do provide some evidence in their support. For instance, see this image of the center of the elliptical radio galaxy NGC 4261 in the Virgo cluster. The HST image of the center of the galaxy clearly shows a torus of gas and dust surrounding a central bright source. Although the supermassive black hole could not be resolved, note that the obscuring torus with a radius of about 70 parsec is normal to the radio jets extending 15 kiloparsec from the nucleus. Such observations strengthen unification theories such as those suggested by Ari and Padovani in the year 1995. Due to their incredible luminosity, quasars can act as standard candles to explore the distant universe. This image shows the galaxy UHZ1 in a composite image with data from the NASA's Chandra X-ray Observatory and the James Webb Space Telescope. The tiny orange speck seen in the JWST image is a supermassive black hole in a galaxy 13.2 billion light-years from Earth, which means the light we see was emitted by it when the universe was just 3% of its present age. That is, just 470 million years after the Big Bang. The purple hazy cloud and most of the galaxies that are seen here are actually part of a foreground galaxy cluster called Abell 2744, which is at a redshift of only 0.3. This is therefore a supermassive black hole in its infancy and at redshift of over 10, the farthest known quasar, at least at the time of the recording of this video. I sincerely hope you would have learned something new about active galaxies from this two-part discussion. Please do like, share and subscribe and let me know what other topics you would like me to cover on this channel. I'll see you next week. Until then, take care.